Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 24th, 2025, about 1 week ago. It introduces a tool called Hermes that mixes informal language model reasoning with strict Lean-4 proof checking, and on hard math benchmarks, it reaches up to a 67% accuracy improvement while using 80% fewer total inference flops. The paper is titled Hermes, Towards Efficient and Verifiable Mathematical Reasoning in LLMs. And as we will see later, the implications for trustworthy, cost-efficient math reasoning are pretty significant. Also, the authors shared a GitHub repo for Hermes, where you can grab the paper PDF, skim a clear, high-level overview of the agent, and check detailed benchmark tables across models and datasets. The README also hints at a LangChain-based implementation and Lean-4 integration docs that are planned for release. Alright, Figure 1 lays out how Hermes actually works, end-to-end. The problem goes into a reasoning language model, which proposes candidate steps in natural language. A translator module turns each key step into Lean-4 code, so the prover module can try to formally prove or refute it. The feedback module then sends a simple success or failure signal back to the language model, which adjusts its next steps. This loop keeps the informal reasoning flexible, while Lean-4 quietly checks the logic. So, while Figure 1 sketched the high-level loop, Figure 2 shows the full Hermes framework with concrete tool calls. The reasoning language model writes an informal step, which enters the translation module that repeatedly auto-formalizes it into Lean-4, compiles it, and back-translates to check semantic match. The prover module then tries to turn that Lean statement into a fully verified proof, again with multiple attempts. The feedback module reads the compiler's true or false signal and either asks the model to revise, self-check, or proceed with generation, so every critical step gets an explicit verification decision. Alright, Figure 2 showed how the agent works internally, and Table 1 now reports how well that setup performs across different models and datasets. Table 1 lists accuracy numbers for 3 base models on 4 math benchmarks, comparing informal methods, reward model selection, and lean-based approaches. Hermes consistently reaches the highest or near highest accuracy in every column, often by large margins. The gains are especially strong on the hardest benchmark HM2, where Hermes with DeepSeek v3.1 clearly outperforms all alternatives. Well, Table 1 focused on accuracy, and Figure 3 shifts to cost, showing how many reasoning tokens each method spends per problem. Across all 3 panels, Hermes stays close to zero-shot chain of thought in token budget, yet stays far below the orange reward-based methods. The gap becomes dramatic on the harder datasets, where reward-based best of 5 needs 3 to 6 times more tokens. So Hermes delivers its accuracy gains without paying a large generation cost. Alright, Figure 3 focused on compute cost, and Table 2 now tests which Hermes modules actually matter for accuracy. The table toggles the memory buffer and the prover model on or off, then reports scores on the math and AIME benchmarks. The full system, with both modules active, achieves about 97% on math and 67% on AIME. Dropping the prover hurts most, especially on AIME, which shows that symbolic verification is crucial for hard, dependency-heavy problems. So the big message is that Hermes shows language models can stay exploratory while getting symbolic reality checks from Lean-4, which sharply boosts both accuracy and efficiency on hard math. More broadly, this kind of interleaved formal verification looks like a blueprint for safer reasoning agents beyond math. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.